In this lecture, we are going to learn about the friction. This term friction isn't new for the students. They have been already studying it in their high school level in quite good detail. So let's have a brief recap of all those concepts which we have already learned in the high school level. So let's read this statement here. Whenever any two surfaces are in contact and either there is a relative sliding or the tendency of sliding between them, then a resistive tangential force acts on both the surfaces equal and opposite against the relative motion called the force of friction or simply the friction. So what does this statement mean here? Let's take an example of the block which has been shown here in the figure. Okay, there is a block B shown in the figure which is resting on a rough surface. Now let us apply a force P here in the positive x direction. If we see the implications of this force on the block, there are two implications. First is that the block will start sliding, obviously in the positive x direction, that is in the direction of the applied force. The second implication is that this force B isn't strong enough to move the block in the positive x direction, therefore it will remain at rest. But still it will have tendency of sliding in the positive direction. That is, there will be two implications. First is that the block will start sliding in the direction of the applied force, and second is that the block will remain at rest, but still it will have the tendency to slide in the positive x direction, which is the direction of the applied force. Now, in both the cases, this sliding or the tendency of the sliding will be resisted by a force that is acting tangential to the contact surface. Okay, let me draw the free body diagram first. If this is the free body diagram, if this is the block B, the forces on the block can be shown here. This is the normal reaction in the upward direction, which is exerted by this surface on the block. The weight of this block can be shown in the vertically downward direction. This is the applied force, and this is the applied force. Then there will be a friction force acting on the contact surface. Now see here, this is the contact surface between the block and the ground. Therefore, this friction force will be in the direction opposite to the relative motion. Opposite to the relative motion or the tendency of the relative motion. Okay, so this is the friction force acting on this block. So this friction force is actually a tangential force. Okay, you can see that I have written the tangential force because it is acting tangent to the surface in the contact. Let me draw the free body diagram of the rough surface here, okay, of the ground. Therefore, the forces on this will be, there will be a normal reaction which will be exerted by the block on this ground. Okay, this is the normal reaction exerted by the ground on the block, and this is the normal reaction exerted by the block on the ground, and they will be equal and opposite. Okay, they will be equal and opposite. Fine. And the friction force again is equal and opposite because it is acting on the both the surfaces in the contact. The lower surface of the block was in contact with the ground. Therefore, if the friction force on the block is in this negative x direction, the same friction force will be, that is the magnitude of the friction force will be same on the on this ground, but that will be in the opposite direction according to the Newton's third law of motion. Okay, so this will be the direction of the friction force on the ground. So therefore, we can read this statement again. Whenever any two surfaces are in contact and either there is a relative sliding or tendency of sliding between them, then there is a resistive tangential force. Okay, again you can see that on this ground, again this force friction is a tangential force. A resistive tangential force acts on both the surfaces equal and opposite against the relative motion called the force of friction or simply the friction. So one more term here is a relative motion. So it is a misconception among the students that the friction force is against the motion. So it is not against the motion, it is actually against the relative motion. If you have observed that we are moving forward, okay, suppose a man is walking on the ground, he is moving in the forward direction, that is his motion is in the forward direction, but the force of friction is also in the forward direction, but his tendency to move is actually in the backward direction. When he puts his foot on the ground, the point of contact tends to move in the backward direction. The point of contact between his foot and the ground tends to move in the backward direction. The friction force is in the forward direction. Okay, So his motion is in the forward direction. Therefore, the friction force is here. The man is able to move forward because of the friction force. Okay. Actually, the tendency of the motion of the man is in the backward direction, but the friction force will be in the forward direction. Okay. So therefore, we have to be careful that it is not against the motion, it is against the relative motion or tendency of the relative motion. One more thing is that in our course, the discussion of the friction will be restricted to the Coulomb friction. This Coulomb friction is also known as dry friction. It is the friction force. It is the friction between two dry surfaces in contact. Okay, it is the friction force between two dry surfaces in contact. Okay, so we are assuming that the contact surfaces are completely dry. There isn't any fluid film between the surfaces. Okay, there isn't any fluid film between the surfaces. Otherwise, we have to bring in the concept of the viscosity. Okay, the fluid friction is defined in terms of the viscosity of the fluid. That thing we have to bring into the consideration, but our discussion here will be restricted to the Coulomb friction, that is the dry friction. Okay, so let's see what is the Coulomb's theory of dry friction. Let me take an example of this block here. Let me suppose that the block is of a weight W that is equal to 100 Newton. If I draw the free body of diagram of this block, this P is the applied force here. Okay, this is the applied force. This is the normal direction and this is the weight of the block. Now this P is either it will move the block in the positive x direction or there will be a tendency of the block to move in the positive x direction. In both the cases, it will be resisted by a friction force in the opposite direction, that is in the negative x direction. Now, if I apply some value of the force P, we can see that the block is at rest. Okay. Now, if I try to increase this force, again, this block is in rest. Suppose I further increase the magnitude. Suppose I apply the force P1, the block remains at rest. After that, I enhance the magnitude of the force P2 is greater than P1, the block is again at rest. If I further increase the value of P3, the block is again at rest. There will be a value of the applied force at which the block will just tend to move. Okay, the block will just tend to slide. Okay, and if I further increase the value of the P, that is P5, the block will start sliding. Okay, the block will be in the sliding motion. So for some values of the P, if I consider these three values, okay, block remains at rest. If I consider this value of the P applied force, block starts to move. Okay, this is simply an example. And if I further increase, the block will be moving. And we can see that P5 is greater than P4, greater than P3, greater than P2, greater than P1. And what is the value of this P4 at which the block is just trying to is just trying to slide? What is the value of this P4 that is at which the block is just trying to slide? Okay, that is the motion is just about to begin. That value of the applied force is known as the limiting friction. The force at which the motion is just about to begin. Okay, the force at which the motion is just about to begin, that is, block is just about to slide. The block will be at rest, but it is just about to slide. So this is the value of the limiting friction, and it is found by the limiting value of the static friction is seen that it is proportional to the normal reaction, and its magnitude is equal to introducing the constant of proportionality, that is mu s, which is the coefficient of the static friction. So this is actually the limiting value of the friction. Limiting value of the friction, that is, if our applied force is of this value, the block will the block will be just about to slide. Okay, the block will be just about to slide. So what happens here is, if I apply this equation to the block here, we can see that the normal reaction is equal to 100. Let me assume that the coefficient of static friction between this block and the ground is equal to 0.3. So if I calculate the value of the limiting friction, that is equal to mu sn, in fact, that will be equal to 0.3 multiplied by normal reaction is equal to 100. Okay, it is equal to the weight, that will be equal to 30 Newton. What is the meaning of this? That is, if I apply force P1 equal to 10 Newton, the block will remain at rest and the friction force will be equal to 10 Newton. Okay, the friction force will be equal to 10 Newton. If I apply P2 equal to 20 Newton, the friction force will be equal to 20 Newton. If I apply P3 equal to 29 Newton, the friction force will be equal to 29 Newton. That is, we can say that the friction force is self-adjusting force, or in fact static friction is self-adjusting. Okay, static friction is self-adjusting. That is, if I'm trying to increase the force, the friction force is getting increased. Okay, and it was the applied force was 10, the friction force was 10. Applied force increased it to 20, the friction force increased it to 20. Applied force increased it to 29, the friction force also increased it to 29. But it won't keep on increasing forever. There is a limiting value of the friction, and after that the block will start to move. At that limiting value of the friction is, suppose in this case it is 30. Therefore, if P4 was 30, the friction force again will be equal to 30, but the block will be just about to slide. Okay, the block will be just about to slide. Okay, now if we apply the force beyond 30, that is 31 Newton, 32 Newton, 33 Newton, the block will be sliding. Okay, the block will be sliding, and the friction in that case will be the kinetic friction. The friction in that case will be the kinetic friction. And kinetic friction is represented by Fk. It is also equal to mu Kn, okay, where mu K is the coefficient of the kinetic friction. And usually mu S is greater than mu K. Okay, mu S is greater than mu K. So after that, if I apply the force of 40 Newton, the friction force still will remain mu Kn. If I apply a force of 50 Newton, the body will be in motion, but the friction force won't be dependent upon the applied force. It will be equal to mu Kn. If I apply a force of 60 Newton or 100 Newton, the body will be moving, the block will be moving, but the friction force will still be equal to mu Kn. Okay, this is the force of kinetic friction. So this is clear from this figure here. You can see that I was applying 10 Newton. Suppose here I was applying 10 Newton, the friction force was 10 Newton. See here, this is the applied force here. in this direction it is the applied force, and here in this direction it is the friction force. Suppose I had applied 10 Newton, the friction force was 10 Newton. I had applied 20 Newton, the friction force is equal to 20 Newton. I had applied 30 Newton, the friction force will also be equal to 30 Newton, but just at this point, the block will start to move and the value of this friction will go on decreasing. Okay, that is kinetic friction. Up to this point, it was static friction, and beyond this, we can say that it is the impending point. At this point, the motion is just about to begin, and once the motion has begun, then what will happen to the force of friction? The force of friction will decrease, okay, because mu s is greater than mu k. Okay, after this point the friction force will be mu kn. Okay, up to this point it was mu k, after at this point it was mu ks. Okay, at this point it was, sorry, mu sn. Okay, at this point the friction force was mu sn, and after that it will be equal to mu kn, and it will start decreasing. So from point o to this point the friction force was self-adjusting. Okay, it was dependent upon the applied force, and once it reached the limiting condition, after that, at this point the friction force was equal to the limiting value of the friction, that was equal to mu sn. After this it is equal to what? Mu kn. Now see here, this is remaining constant because this friction force now is equal to mu k, and that is the coefficient, that is the kinetic friction. Okay, you can see that this is the kinetic friction. Okay, so hope this figure is clear to the students. So this is the point of the impending motion. Okay, impending motion is the point about which, at which the block is just about to slide. Okay, at which the motion is just about to begin. Okay, so this is regarding the laws of the friction. So we can just summarize whatever we have learned in the 3 points. The first point is that if applied force is, if the force applied is less than the limiting value of the static friction, okay, you can see that the limiting value of the static friction is equal to mu sn. Okay, if the applied force is less than the limiting value of the static friction, then what will happen? The body will remain at rest, and the friction force, okay, this is the friction force, that will be equal to the applied force. Okay, that friction force will be equal to the applied force. Now the second thing is that if the applied force is equal to the limiting value of the static friction, then we can say that the block is just about to slide, that is impending motion, and the friction force here will be equal to the limiting value of the static friction. Okay, the friction force will be equal to the limiting value of the static friction, that is, it will be equal to mu sn. Okay, we have to be careful when we have to use this equation, that is, static friction is equal to mu sn only in the case of the impending motion. Okay, you can see that in the first point I have written that if the applied force is less than the static friction force, that is the limiting value of the static friction, then the friction force will be equal to the applied force, not equal to the mu sn. Okay, and the third condition is that if applied force is greater than this limiting value of the static friction, then the body will be in the motion. Okay, the body will be in the motion, and the friction force here will be equal to the kinetic friction. Okay, it will be equal to the kinetic friction, whose coefficient of friction is equal to mu k. Okay, so this is the summary of all the things which you have learned up to this point. Okay, so let's define some more concepts. So one concept is the angle of friction. Okay, to see what is the angle of friction, let's see the schematic here. Let's first of all define the angle of friction. It is the angle made by It is the angle made by the normal reaction it is the angle made by the normal reaction between the resultant of, in fact we can write it with, it is the angle made by the normal reaction with the resultant of normal reaction and the friction force. At impending motion. So if this is a block, it has been, there is a force P which is applied to this block. Okay, this is the weight of the block. This will be the normal reaction of the block, and this is the friction force shown by the blue color. This is the friction force shown by the blue color. Then this is the resultant of the normal force and the friction force. Okay, you can see that this arrow shown by the black color here is the resultant of the friction force and the normal force. This is the resultant here. And what does this resultant make with the normal reaction? That is known as the angle of friction, and it is denoted by phi. But at the case of impending motion, okay, again at the case of impending motion, so from here we can see that from this right angle triangle we can see that tan phi is equal to, okay, it will be equal to perpendicular by base, that is it is equal to friction force divided by the normal reaction. And since it is the case of the impending motion, we can write here that it is equal to mu Sn. Okay, only in the case of the impending motion I can say that the friction force is equal to mu Sn divided by n. So from here we get that tan phi is equal to mu s, and from here we get that the angle of friction is equal to the tan inverse of mu s. Okay, it is the tan inverse of the coefficient of static friction. So this is how we define the angle of friction. Another term that we need to see is the angle of repose. So angle of repose is the angle at which, angle of inclination of the plane, okay, it is the angle of inclination of the plane at which the block will just tend to slide down. Okay, you can see that there is a block which is on the inclined plane, and what is the inclination? Theta r. Okay, at which inclination this block will be just about to slide down the inclined plane. Okay, there will be some inclinations at which the block will remain at the inclined plane, and as we go on increasing the inclination of this inclined plane, there will be one angle at which the block will just try to slide down the inclined plane. Okay, that is the impending motion. We have to see the case of the impending motion. So what is this theta equal to? If this is the weight of this block, we can say that this is the cos component and this is the sine component. This is the normal reaction. Okay, I can show it by n. This is the normal reaction and this is the friction force. Since the tendency of this block, the block isn't moving, but it has a tendency to go into the down the plane. Therefore, the friction force will be equal to acting in the up plane. Okay, and since this is the case of the impending motion, this will be equal to mu Sn. It will be equal to mu Sn. Okay, so angle of repose is actually the inclination of the inclined plane. It is actually inclination of the inclined plane at which the block is just about to slide down. it is the case of impending motion. Since impending motion case is also the case of equilibrium, because it is not moving, it is just about to move, therefore we can use the equilibrium equation. We can see that in this that normal reaction will be equal to W cos theta, and friction force will be equal to W sine theta, and this friction force can be written as mu n. It will be equal to W sine theta. This normal reaction is equal to W cos theta, therefore mu s, in fact, this will be equal to W sine theta. The weight term will cancel out, and we will be left with mu s is equal to tan theta, and this is a particular value of theta, that is the theta r. Okay, it is the theta r, that is the angle of repose. Okay, so this is actually the angle of repose. Okay, from here we can get the angle of repose, that will be theta r is equal to tan inverse mu. Okay, this is the angle of repose. So in the previous slide we had obtained one relation that friction angle is equal to tan mu s, and here we can see that theta r is equal to tan inverse mu. So we can conclude that friction angle is equal to angle of repose, but at only at the impending motion. Okay, at impending motion, the friction angle is equal to the angle of repose. So let's see one brief problem. This is one solid example in our RC Hibbeler text. A uniform 10 kg ladder rests against a smooth wall. Okay, you can see that this is the wall and this is smooth. Therefore, the coefficient of friction here will be 0. Therefore, there won't be any friction force on this wall between this end of the ladder and the wall. And the end A rests on the rough horizontal plane, for which the coefficient of static friction, okay, mu s is given here. That is, it is equal to 0.3. Determine the angle of the inclination of the ladder and the normal reaction at B if the ladder is on the verge of slipping. Okay, you can see that at this instant the ladder is just on the verge of slipping. That is, the point A can go in the right direction and the point B will come down. Okay, sorry, point A will go in the left direction. That is, the motion of this A will be towards left, and the motion of this B will be towards and downwards. Okay, because it is at the verge of slipping. But still, in this case, it is still at rest, but it is at the verge of slipping. Okay, if we lower the inclination the beyond this, okay, if we lower the inclination beyond this ladder will slip. But still, in this case, it is at rest, but it is in the case of the impending motion, that is, it is about to slide. And at which angle it is about to slide, that angle we have to find out from this. Okay, we have to find out the angle about which at which it is about to slide. So we can draw the free body diagram of this ladder. We can see that on this ladder there will be a normal reaction which is exerted by this wall. This is the normal reaction at B. Similarly, there will be a normal reaction at A. And since this is about to slip, the point A is trying to go in the left direction. Therefore, the friction force has to be towards right. This is the friction force. Another force will be the weight of this ladder that will act at the center of gravity. This is the weight of the ladder. Okay. So let's see. This is all regarding the free body diagram. Therefore, here there will be no friction because it is a smooth wall. Here we have three unknowns. One unknown is NB, another unknown is Na, and this is not an unknown because it is this friction force is in the limiting condition will be equal to mu SNA. Okay, it will be equal to mu SNA. That is friction force at A. It will be equal to mu SNA. Why mu SNA? Because it is the case of the impending motion. Only then we can use this equation that friction force is equal to the mu SNA. Okay, we can use this equation. Therefore, this friction force is dependent upon Na. Therefore, it is not an independent variable. Okay, the independent unknowns are here Na, Nb, and this theta. Okay, actually, we are interested in finding the value of theta. So we can use the summation of the forces in the x direction to be 0 for equilibrium, okay, because it is in rest, but although it is in impending motion, but still it is at rest, okay. Summation of the forces is equal to 0. We can see that in the x direction, the friction force is acting in the positive x direction and NB is acting in the negative x direction. Therefore, friction force will be equal to NB. And since this friction force is equal to mu Na, okay, this is the coefficient of the static friction. So from here we get that NB is equal to mu S is equal to 0.3. Therefore, NB is equal to mu SNA. This is the first equation. We can apply the equilibrium condition in the y direction. Summation of forces in the y direction should be equal to 0. Now in the y direction, the forces are Na is in the upward direction minus the weight of the slider is in the downward direction. So this has to be 0. Therefore, Na should be equal to the weight of the slider. Now the mass of the slider is given, that is it is equal to 10 into 9.81. So normal reaction at A should be equal to, it should be equal to 98.1, and it will be in newtons. Okay, now the third equation, since this ladder is a rigid body, therefore we can use the equilibrium condition as well, that is the moment equation, taking summation of the moments about any point to be 0, but here it will be quite easy to take the summation of the moments about A to be 0. Okay, so about A we can see that this friction force and the normal reaction, they don't create any moment. The weight will create a moment in the clockwise direction and NB will create a moment in an anti-clockwise direction. Okay, so we can see these distances here. We can see that this distance, I can draw the figure here. This is 4 meters, this is theta. Okay, so this will be equal to 4 sine theta, and this will be equal to 4 cos theta. NB is acting here. Therefore, for the force arm for NB force will be equal to 4 sine theta, and for the weight, it will be the half of this. That is, if this is complete 4 cos theta, then the half will be equal to 2 cos theta. Okay, so summation of the forces about A should be equal to 0. Then we can say that NB will create an anti-clockwise moment whose magnitude is equal to NB into 4 sine theta. W will create a clockwise moment, that is, it will have the opposite sense, therefore W into 2 cos theta. This should be equal to 0. Okay, so from here we can get that 4 NB sine theta, that will be equal to 2W cos theta. Sine theta by cos theta will be equal to tan theta, and from the right hand side we can have 2 into W, that is the weight is equal to 98.1 divided by 4 NB. that is 4 into NB, I think from this equation was equal to 0.3 Na. Okay, it was equal to 0.3 Na. So 0.3 Na, Na value was equal to 98.1. Okay, so after solving this, we can get that tan theta is equal to, it will be equal to 1 by 0.6. Okay, it will be equal to 1 by 0.6. It will be equal to, so from here we will get that theta is equal to roughly around 59.5 degrees. So at this inclination, okay, at this theta, the ladder will be just about to slip.